So till now we have already discussed about Sn1, Sn2 and E1. Now we are going to do E2 reaction, but before that I'll summarize all the three reactions so that you can understand the difference between all the four different type of reactions. So first we will discuss type 1 reaction. So type 1. So what do we mean by type 1 reaction? Type 1 reactions are Sn1 reaction and E1 reaction. Okay. For both of them, what is important? First of all, both of them are called as unimolecular reactions. Unimolecular reaction, right? Why? Because the concentration of reactant will decide on the rate of reaction. So we can also write it as rate of reaction is directly proportional to the concentration of the reagent or the reactant. Okay. Now apart from that, what is the another important factor? That both of the reactions require weak attacking agent. So basically it can be a weak base or a weak nucleophile. Right? Now other factor. Now what is the other important thing? Other important thing is Sn1 and E1 both can take place in the same reaction mixture. What will be the deciding factor to decide whether the reaction will go through Sn1 or E1? That is temperature. Higher the temperature, more will be E1 product. So less temperature favors Sn1. So in the same reaction mixture, we can get Sn1 product as well as even product. As well as what we have, though so many things are same for Sn1 and even the mechanism is. So let's quickly see the mechanism, how the mechanism of even works and Sn1 works. So basically we will have a chain where the leaving group is present. Now we have an attacking agent which can be a base or a nucleophile. Okay. Now depending upon the temperature and the kind of attacking agent we have taken, we will decide whether the reaction will go through Sn1 or even. If the temperature is high, reaction will go through E1. If the temperature is low, reaction will go through Sn1. Okay, so now what will happen in both the cases? This base or nucleophile will wait for leaving group to leave because these are weak nucleophile or a weak base and weak nucleophile and a weak base as compared to the leaving group present over here. So they will wait for leaving group to leave and the carbocation will be formed. So this is the carbocation will be formed in both the cases, right? If the rearrangement is possible, rearrangement will happen for this carbocation to make it more stable carbocation, else the attack will happen. Now in case of even, how the attack will happen in case of even, we will look out for the hydrogens present on the beta position, mark it beta 1, beta 2, and this is my carbocation. So my base will attack on the beta hydrogens, right? Either on the beta 2 or on the beta 1 to form the respective alkene. So the alkene formed will be, so they will abstract these hydrogens. If the hydrogen will be abstracted from the beta 2 position, the alkene will be formed like this. If the hydrogen is abstracted from the beta 1 position, alkene will be formed like this. Now we already know what is Sn2 rule. Sn2 rule means when the base attacks on the beta hydrogen, the beta carbon should be more alkylated, or you can say the alkene form will be more alkylated alkene when a small base will attack on the beta carbons. Okay, so here, which one is more alkylated beta carbon? The beta 2 is more alkylated beta carbon, and hence it will give you the Sn2 product which we expect, and that will be more stable product also. So alkene which is more alkylated is always more stable because it is capable of forming more hyperconjugating structures. So this is my Sn2 product which is major, and this is my Hoffman product which is minor. We have already discussed this in much more detail, right? This is about my even reaction, whereas in Sn1 reaction, rather than attacking onto the beta hydrogens, it will directly go and attack on the carbon where the carbocation has been formed and will get attached over there. So we will get a nucleophile present over here. Now when we talk about the stereochemistry of this molecule, when the substitution has taken place, it will be forming racemic mixture. right? And in this case, this reaction is a regioselective reaction. Regioselective. What do we mean by regioselective? Regioselective means it selects the region, or it selects the region in the carbon chain where the reaction will happen maximum, or you can say a particular type of isomer of an alkene will be formed in the major quantities as compared to the other alkene, other isomeric alkene. So that kind of reaction is called as regioselective. So basically this and this, these two alkenes are isomers of each other, but this isomer will be formed in the major quantities, and that is why the reaction is called as regioselective. Now for both of these reactions, when we talk about rate with respect to the carbon where leaving group is present, rate of reaction will be tertiary, then secondary, and then primary. Right? So this is the reaction. This is the mechanism of E1 and Sn1. So we have summarized this, and I hope you would be able to recall what we had done in Sn1 and E1. Now let's quickly see what was there in Sn2 so that we can relate it with E2. So basically I'll be doing Sn2 and parallelly I'll be doing E2 also, so that you can easily compare both the reaction mechanisms and you'll be understand where the difference comes. When you'll have to compare the reaction, when a reaction is given to you and when you have to compare, or when you have to figure out whether it's Sn2 or E2, you should be able to do it. So let's quickly see the Sn2 mechanism and parallelly do E2 mechanism. Now let's do the second part, that is type 2 reactions, where we have already done Sn2, which is called as bimolecular substitution reaction. In fact, our E2 is also called as bimolecular elimination reaction. Right? For Sn2, we had already discussed this, or we have already seen that we require a strong nucleophile. That strong nucleophile doesn't wait for leaving group to leave. Instead, it will attack on the carbon directly, will kick out the leaving group, and will form the product. So very similar to this, we require a strong base for E2 reaction to take place. So what do we require for Sn2? Strong nucleophile. And for E2, we require strong base. So we have already seen variety of strong nucleophiles. Let's talk about the strong base. So what all different strong base we have? Alcoholic KOH. Wherever you will see alcoholic KOH, just understand the reaction is going through E2. Similar way, alcoholic NaOH. Right? Next set of reagents, NaNH2 in presence of NH3. This is also a set of very strong base. So this is even stronger than your alcoholic KOH and alcoholic NaOH. And third set of reagents, what we will see is RO minus in the presence of ROH, or in the presence of RO minus in the presence of ROH. So, and the fourth kind of base, which is very similar to this, or you can say the same variant of this, and that is O minus. So basically this is my tert butoxide, and it is very strong base. If you remember, we have already discussed about some category of bases which are strong bases but weak nucleophiles. So this is very strong base but poor nucleophile. So whenever you will see this kind of reagent, this will always go through E2 but not Sn2. So here, especially in this case, there will be no competition for Sn2 and E2. Okay. So these are our strong bases. So what all we have seen, that Sn2 and E2 both are biomolecular substitution and elimination reactions. For Sn2 we require strong nucleophile. For E2 we require strong base. What are different strong bases we have? Alcoholic KOH, alcoholic NaOH, NaNH2 in the presence of NH3, RO minus in presence of ROH, and we have tert butoxide in the presence of tert butyl alcohol. Okay, so these are very, very strong bases we have. Now let's see how the mechanism similarity is there between between Sn2 and E2. So let's see Sn2 mechanism. In case of Sn2 mechanism, what we used to do is we used to take a leaving group and a nucleophile. right? And this is the very, very strong nucleophile. So this strong nucleophile will not wait for this leaving group to leave. Instead, it will directly attack on the carbon where the leaving group is present from the opposite direction and used to form a transition state like this, where the leaving group is leaving and parallelly the nucleophile is forming a bond with the carbon, and we used to call it transition state in concerted fashion. So what does the concerted fashion or concerted reaction means? Where the transition state in which the leaving group, in which a particular bond is breaking and the other new bond is forming. So basically existing bond is breaking and the new bond formation is happening simultaneously. That kind of reaction is called as concerted reaction. So this transition state used to exist in the concerted fashion, where the existing bond between carbon and leaving group is breaking, whereas the new bond between nucleophile and the carbon is forming. Now after this, new leaving group used to leave completely. Leaving group used to leave completely, and we used to get a nucleophile over here. And the product used to have inverted configuration. And one more important thing which you have to notice over here is no carbocation formation used to happen. So no rearrangement. Right? So this was the mechanism what we had done in Sn2. Very, very similar mechanism we have in E2 also. So let's quickly see how the reaction happens in E2. I'll just rub this off and write the E2 mechanism. Try to relate it with the Sn2 mechanism what we have seen just now. So we have, instead of strong nucleophile, now I have a strong base over here. Okay. Let's rub this part also. And let me just rub this transition state also and the final product. Now we will see what change will happen in the transition state if the base is attacking. Now when the base has to attack, again base will not wait for this leaving group to leave. Rather than that, it will directly attack, because it is a very, very strong base. It will attack on the carbon and remove the hydrogen. So base job, what is the difference between base and nucleophile? Nucleophile will attack on the carbocation, whereas base will pull out the hydrogen, acidic hydrogen. So there will be one hydrogen present over here and one hydrogen present over here. So we have basically two hydrogens here, one here and one here, and similarly three hydrogens over here. Right? Now let's mark this as a beta 2 and this is as a beta 1. Okay. So now when the base will attack, base has two probable positions where it can attack. It can attack on beta 1 to remove the hydrogen, or it can attack on beta 2 to remove the hydrogen. Okay, let's see what will be the transition state formed if the removal of hydrogen is happening from beta 1. Okay, and then in the next step we will see removal of hydrogen from beta 2. Okay, both the intermediates we will see, both the transition states we will see. So in the first case we are assuming that the hydrogen removal is happening from the beta 1 position. So this hydrogen will get removed. Okay, but it will not get removed immediately, though in this process again the transition state will be formed in such a way that the leaving group would be leaving, and at the same time beta hydrogen will be removing from the beta position. Okay, so basically the bond between carbon and the leaving group would be breaking, as well as the bond between carbon and hydrogen from the beta position would be breaking, and the bond between hydrogen and base will be forming. Okay, so this reaction is also in the concerted fashion, because a new bond is forming. New bond is forming between beta and between base and hydrogen, as well as a new bond is forming between beta carbon and the alpha carbon. So this is the new bonds. These are the new bonds forming. One is this pi bond is forming, and another is the bond between base and hydrogen is forming. Whereas the bond between this hydrogen and this beta carbon is breaking, and the bond between this carbon and leaving group is breaking. So this reaction also happens in the concerted fashion. So this transition state has few bonds forming and few bonds breaking simultaneously. So no carbocation will be formed, no rearrangement will happen, exactly in the same manner how it was in the E2. Now similar way, rather than if I do the removal from beta 2 position rather than removing from beta 1, how my structure will look like, or how my transition state will look like. So here the hydrogen sorry. So hydrogen will be breaking its bond with the carbon, whereas the new bond of hydrogen and base would be forming, right? And the leaving group would be leaving. And this carbon would have gained partial negative charge. This carbon would have got a partial positive charge. So partial double bond character would have been already appeared in this transition state. Transition state. Okay, let's mark it transition state 1, and this is transition state 2. Now just observe and analyze that which transition state seems to be more stable. In the first transition state, what is happening is the hydrogen bond is breaking from the carbon, which is less alkylated carbon. So now in the transition state, double bond character has already started appearing. So more stable alkene will be, more stable the transition state will be. So in this case, what is happening? The alkene which is forming is a less stable alkene. Why? Because it is less alkylated. So this transition state is going to be less stable as compared to this. Why this? Because in this case, if you'll see what is happening, the double bond which is forming between the carbon which is more alkylated and the alpha carbon. So more alkylated alkene is about to form, more stable will be the transition state. So which one is more stable? Transition state 2 is more stable than transition state 1. Hence, the reaction will go through this pathway rather than going through this pathway. So this pathway it will not follow, rather than that it will follow this pathway. Or you can say the major product will be formed by transition state 2 and the minor product will be formed by transition state 1. We also call the more alkylated alkene as a we also call the more alkylated alkene as a Sn2 product, and the less alkylated alkene as a Hoffman product. So we have already discussed about Sn2 and Hoffman in even reaction. So in even also Sn2 used to be the major product, and in E2 also Sn2 is going to be the major product and Hoffman is going to be minor product. So the product formed after this will be this and this, and this is going to be Hoffman product. This is going to be Sn2 product. This is going to be in the minor quantities and this is going to be in the major quantities. So let's quickly see again what happened in the E2 reaction. We had a leaving group present here. We had a strong base over here. Strong base didn't wait for leaving group to leave. Rather than that, it started attacking on the beta hydrogens. We had two beta positions. One is this beta 1 and this is beta 2. If the attack happened on the beta 1 position, the hydrogen removal will happen and the alkene form will be less alkylated alkene. In the transition state, a new bond would be forming and the old bonds would be breaking. The bond between carbon and leaving group and carbon and hydrogen would be breaking, whereas the new bond between carbon, alpha carbon and beta carbon would be forming, that is a pi bond, and the new bond between base and hydrogen would be forming. Okay. Similar way, if the removal is happening from the beta 2 position, in that case the bond between beta 2 and beta 2 carbon and hydrogen will be breaking, and the bond between leaving group and carbon would be breaking, whereas a new pi bond would be forming between beta carbon and the alpha carbon, and the final product form would be the Sn2 product. So this is single step reaction. So both of our reactions, Sn2 and E2, both are single step reactions, right, and go through only one transition state. So when we will see the graph, the potential energy diagram of both of them, the potential energy diagram will look like this. We have discussed about the potential energy diagram in detail in case of Sn2. So exactly same potential energy diagram will be formed in E2 also. This is the reaction coordinates, and this is the energy. Right? This is, let's just make it like this. So this is my Rx plus base, and this is my alkene, and this will be the energy of the transition state. Got it? So this will be the potential energy diagram followed by E2 as well as Sn2. Now we have seen a lot of similarities between Sn2 and E2, but what is the difference between Sn2 and E2? In case of Sn2, the carbon where leaving group is present, that also used to decide the rate of reaction, and the rate of reaction of Sn2 used to follow the order of primary, secondary and tertiary. That means primary will show the fastest reaction towards Sn2, whereas the tertiary will show the slowest reaction towards Sn2 reaction. Many times we also say that tertiary won't show Sn2 reaction at all, whereas in case of E2, so I'm just writing it over here, in case of E2, rate of reaction with respect to the degree of carbon, with respect to the degree of carbon where leaving group is present is tertiary, secondary and primary. Yes, it is tertiary, secondary and primary. How? See, we had already discussed when the transition states are forming, which transition state we said is more stable than the other one. Transition state 2 is more stable than transition state 1. Why? Because the alkene which is going to form after transition state 2 is the more alkylated alkene. And that is going to be more stable alkene. Whereas in case of transition state 1, the alkene which is going to form is a less alkylated alkene and hence is going to be less stable. So that means we require to remove hydrogen from the carbon which is more branched or which is more alkylated. So reaction will be fastest if the transition state will be stable. So transition state will be stable only when the hydrogen is getting removed from the more branched carbon. So here also it will be tertiary, secondary and primary. So any carbon, if the carbon is tertiary and we have to remove the hydrogen from there, the reaction will be fastest. And if the beta carbon is primary and we have to remove hydrogen from there, the alkene form will be a less stable alkene and hence the rate of the reaction will be slower. So what we have got now, we have got that Sn1, E1 and E2, all the three follow same rate of reaction order, that is tertiary, secondary and primary, whereas my Sn2 follows primary, secondary and tertiary. So it is very easy to figure out Sn2 reaction. Why? Because Sn2 will be able to show the fastest reaction with primary, whereas tertiary will be able to show the fastest reaction towards E2 also, E1 also and Sn1 also. Now in case of secondary, it is a very, very confusing state when secondary compound comes, because in that case you won't be able to identify, it will be difficult to identify whether the reaction will go through E1 or E2 or Sn1 or Sn2, and we will have to look at the multiple factors what we are discussing slowly in each and every type of reaction. Okay, so this is about E2. Now let's discuss more about E2. So when we are talking about E2, let's quickly write down the small details of E2 reaction. So now we will write down the important points about E2. First point, it is bimolecular elimination reaction. Second, it requires strong base. Third, it is single step reaction. Single step reaction goes through a transition state with no carbocation formation. Correct? Fourth, this is an anti-elimination. I will explain you what is anti-elimination just after this. This is important. Make a note of it that we have to discuss this. And the fifth one, this is a regio-selective reaction. We have already discussed what is regio-selective selection, which selects the region where it wants to react, or where which product of the in a carbon chain where the double bond should form and which product should be major. So basically it will be capable of forming two different alkene chains, but out of that one isomeric alkene will be major in quantities and other will be in minor. So we have discussed that Sn2 product will be major and Hoffman product will be minor. Sn2 and Hoffman, both products are going to be isomeric alkenes. And we have a selectivity, or we have to choose, or the reaction chooses itself that which isomeric alkene is going to be major and another is going to be minor. So that kind of reaction is called as regio-selective reaction. Sixth point, it is stereo-selective reaction. And seventh point, it is stereo-specific reaction. So we are also going to understand these two terms, that what is stereoselective reaction and what is stereospecific reaction. So we'll be going to cover up these three things just after I'm done with the writing important points. 8th important point, rate of reaction is directly proportional to the concentration of reactant. We have already discussed this. Order of the reaction is rate of reaction, I'm sorry, I missed this point. Rate of reaction is directly proportional to the concentration of reactant and the concentration of base, both. That is why it is called as bimolecular elimination. Now, order of reaction is 2, molecularity is also 2, and rate of reaction with respect to the carbon where leaving group is present, rate of reaction with respect to the carbon where the leaving group is present is tertiary, secondary and primary. So I have listed down all the important points, what are required to understand or what are required to remember to figure out whether the reaction is E2 or E1 or Sn1 or Sn2. Let's quickly see what is anti-elimination now. Now I'll explain you the anti-elimination in detail, and this is very, very important point when we are talking about E2, and this is something which you have to be really careful about when we are doing the elimination reaction, specifically E2. Okay. Now let's understand what is anti-elimination. So just understand carefully. So this is, we are talking about anti-elimination. Now assume we have a structure like this. See, this is my leaving group, okay, and here is my hydrogen, this is my beta carbon. So this is my beta carbon, okay, and here is I have hydrogen, this is hydrogen and hydrogen, okay. Now if base has to attack on it, now what base wants? Base wants to remove the beta hydrogen. Now if this base will come from here to remove this hydrogen, what will it face? It will face the repulsion, and hence will not be able to approach this hydrogen and will not be able to break it. So it will not be able to do so. Rather than coming from this direction, if this base approaches the beta carbon from this direction and try to abstract this hydrogen, it will be easier for it. Why? Because no repulsion over here. Because see, base is also electron rich species and our leaving group is also an electron rich species. So both will repel if the base will come from the same direction. So now what base has to do? Base has to come from the opposite direction to pull out the hydrogen which is in the opposite direction with respect to the leaving group. So this kind of alignment of hydrogen and leaving group which is opposite to each other is called as anti-positioning. Okay. So here what do we want? So the hydrogen which will be present on the opposite position with respect to the leaving group, that will be removed when a base will attack. The hydrogen which is aligned to in the same direction where the leaving group is, or in the same positioning where the leaving group is, it will not be able to, their base will not be able to remove this hydrogen. Okay, so this kind of positioning or removal of leaving group and hydrogen from the opposite positions is called as anti-elimination, and this is a must condition for E2 reaction to happen. So hydrogen which is present in the same direction where the leaving group is in a plane, it will not get removed, whereas the one which is in the opposite direction will get removed from the base. And why does base do that? Because base wants to avoid the repulsions which will happen between base and leaving group if base will approach to the beta carbon. Okay. So now the removal will happen in such a way that the alkene will be formed like this. So this will be my hydrogen over here, and this will be the things like this. So this is how the alkene will be formed. So hydrogen from here, hydrogen from this position, and leaving group from this position will be removed. So this kind of elimination is called as anti-position, and this is a must. If we do not have hydrogen on the anti-position, the removal will not take place. So let's look at an example. For example, if I have a molecule like this. Okay, now assume I have two R groups over here. Okay. and a CH3 over here and a Br over here. Correct? Now I have, let's say, hydrogen. This is CH3 and Br have been put onto the wedged bond. That means it is towards the viewer, whereas both of the hydrogens are away from the viewer. Now this kind of configuration is cis configuration. All of you understand this is cis because both of the hydrogens are away from the viewer and both are in the same direction. So this configuration is going to be cis. Now if my base has to attack, my base will go from the back side away from the viewer side and will remove this hydrogen. So if this is Br here, I have two beta carbons. One is this as a beta carbon, beta 1, and this as a beta carbon, beta 2. So now where from which all positions my hydrogen can be removed? From beta 1 and beta 2. If the removal will happen from beta 1, this hydrogen will get removed, which is on the opposite direction with respect to the Br. So when base will attack, this will be my product formed. This is R and CH3 over here. Alkene will be formed here. Okay. One is this product when the hydrogen is removed from beta 1 position and bromine has been removed from the alpha carbon. Other possible product is removal of hydrogen from here. Now the hydrogen which is away from the viewer will be removed with respect to the bromine and alkene will be formed like this. Now which will be the major product? This product, the one where the hydrogen removal has happened from the beta 1 position, will be the major product. Why? Because this carbon is the more alkylated carbon. So this is my SADEF product formed, which is major. And this is Hoffman product formed in the minor quantities. Okay, so we have understood what is the anti-removal. Anti-removal means the hydrogen which is on the opposite plane with respect to the bromine will be removed. Now this kind of product formation where one particular type of alkene isomer is major and other is minor is called as regioselectivity. And one specific type of stereoisomer of a product is in major quantities, that is also called a stereoselectivity. So this is my stereoselectivity. Why we have called it stereoselectivity? Because one particular type of isomer if one particular type of stereoisomer of the product is major. Okay. Now, what is stereoselectivity? Stereospecificity. We have already spoken about selectivity. Stereospecificity. Stereospecificity is the term which we use for the reactant, not for the product. So what happens in the stereospecificity? I'll explain you this with the help of an example. Okay. Now let's look at the example. What I had taken here is a cis configuration, right? And the base could react with the species and could pull out the hydrogen which was on the anti-position with respect to the bromine and could form the products, right? Now let's take the same example but in a little different way. Now assume I have CH3 and hydrogen alignment like this. Now instead of bromine on the wedged bond, assume it is on the dash bond and the hydrogen is on the wedge bond. Okay, now assume this is the setup and now my base has to react or now my base has to attack. Okay, or let's do one thing. I'll just remove this hydrogen also. And let's make it more alkylated over here. Let's make it RR over here to understand this more properly. So now this configuration is what type of configuration? This is trans. This cyclic ring is now trans. right? Now see whether the base will be able to remove hydrogen or not. So what will happen? Now base will try to remove this. So what will happen? The base will try to form the bond with hydrogen, or will try to abstract this hydrogen, and bromine will also get removed. That's what happens in the transition state, that attack of base happens on the beta hydrogen, removal of leaving group happens, and then the pi bond forms. But here, will this base be able to even attack on this hydrogen to remove it? No. Why not? Because look at the direction of bromine and hydrogen. Both of them are in the same direction. So if bromine would try to approach this hydrogen, will get repelled by Br. Why? Because this is also electron-rich species, this is also electron-rich species. Both will repel each other, both are like type of molecules, and they'll repel each other, and hence this base will not be able to even approach this hydrogen. What all beta carbons it has? This is one beta carbon, and this is another beta carbon. Right? Let's assume this is beta 1 and this is beta 2. Now beta 1, the base cannot approach this hydrogen because it will get repelled by bromine. Look at the beta 2. Does this beta 2 has any hydrogen in it? No, it doesn't have any hydrogen. So this base will not be able to remove this hydrogen, nor it can approach to beta 2 to remove any hydrogen because there is no hydrogen. So will reaction take place here? No, reaction will not take place here. So when we took the trans kind of setup, the reaction couldn't happen. Now if I'll take cis molecule of it, what will happen in cis? Let's take the cis structure of it. Now I have CH3 here, and hydrogen is on the dash bond. Now again hydrogen is on the dash bond and my bromine is on the wedge. Now when the base will attack, what will happen? Now base can go from the back side, can attack on this hydrogen, can pull out this hydrogen, simultaneously bromine will leave from the front side, and it will be able to form alkene over here. So it has two beta carbons. This is beta 1, beta 2. Beta 2 cannot participate in the reaction, but because it doesn't have hydrogen, so the reaction will happen only with beta 1, and the removal of this hydrogen will take place because it is in the opposite direction with respect to the bromine. So this double bond will form and the reaction will take place. So the product will be your final product. Okay, so what did we see? When we did the same reaction with cis molecule, reaction could happen. But when we took the trans reagent of the same molecule, we couldn't do the reaction. So that means even this reaction is quite selective or specific about what reagent we have taken. What is the stereochemistry of the reagent? If this was the stereochemistry, then the reaction was not happening. When it was cis, the reaction was happening. So this specific thing, the selection or being very specific about the reagent what we have taken, a reaction, if the reaction selects or is specific about a specific type of reagent for reaction to proceed, then the reaction is called as stereospecific reaction. So this is about stereospecificity of the reaction. So stereospecific is related to reactant, whereas regioselectivity and stereoselectivity both are related to product. That means in case of regioselectivity and stereoselectivity, specific stereoisomer or structural isomer product is major. Okay, when we talk about regioselectivity, we are basically talking about structural isomer of a product, and when we are talking about stereoselectivity, we are talking about the stereoisomer of the product, which will be major. Whereas when we are talking about stereospecificity, specific kind of or specific isomer of reactant will be able to show E2 reaction. I hope you would have understood what is anti-elimination, what is regioselectivity, what is stereoselectivity, and what is stereospecificity. So you have to understand that E2 is regioselective, stereospecific, and stereoselective, all the three things. Okay. And next and second important thing, that here also our Sn2 product is major unless we have one case where the Hoffman product will be major. Let's quickly check where the Hoffman product will be major. Just note this down very quickly. Now, we know this, that in case of E1 and E2 both, Sn2 product is major. But there are very few cases of E2 where Hoffman will be major. What all those cases we will discuss now. Before that, first you have to understand what all different bases we can take. Again, I am just talking about what all are the strong bases. So we have different type of bases. Anything which is negatively charged is a base, and the strongest base is with C minus, then comes your N minus, then comes your O minus, and then comes your X minus. So this is how the basic order is. When we are talking about X minus, your I minus, your F minus is the strongest base, then comes your Cl minus, then comes your Br minus, and then comes your I minus, right? When we talk about the leaving group capability of halogens, I minus is the best leaving group, then comes your Cl minus, then comes your Br minus, and then comes your I minus. Sorry, then comes your F minus. So better the leaving group is, faster will be the reaction. Better the leaving group is, all the reactions will be faster, Sn1, Sn2, E1 and E2. So we need a good leaving group for any reaction to proceed further. Okay. So now let's discuss the case where Hoffman will be major. So I had told you there is one base which we had spoken about before, which was a very good base, but weak nucleophile, and we also call it as a big bulky base. And what is it? Tert butoxide. That is tert butoxide. How does it look like? It looks like this. So this is your tertiary butoxide. Right? Now in this case, just look at it. This is a very bulky base also. So when it has to attack on a carbon chain, its own bulkiness will stop it in entering into that zone and pulling out the hydrogen where there are more carbons present. So for example, let's take the structure like this. Okay, this is my leaving group, and this is my beta 1 hydrogen, and this is my beta 2 hydrogen. Okay, now this base has to go and attack on this hydrogen or attack on this hydrogen. It has two possible options. Now what will happen when this base will try to go and abstract this hydrogen on the beta 1? This will get a steric hindrance from this carbon and its own bulky nature, and it will create steric hindrance for itself by its own big size. So it will get repelled and little hindered by this carbon chain, this carbon, right? Whereas if it will attack on the beta 2, it can directly go. There is no other chain over here. So this is the only chain what it has. So it can come from the other direction, which is very free area. It can come from there. It can pull out this hydrogen, and its own bulky structure will not hinder it from removing the hydrogen. I'll repeat it again. So what is happening? It is quite big in structure. So when it will try to enter and try to remove the hydrogen from here or try to form a bond, what will happen is this carbon, these are the three carbons. So causing a little steric hindrance to its own bulky structure. So it will get hit by this carbon. So when it will move over here, it will try to break this bond, or will try to form a bond. It will get little repelled by this and this carbon. as well as a bit of this carbon also. Okay, but when it is about beta 2, it can come from this free area. It can come from this free area and can start forming a bond, and this one whole chain is one side, and it can come from the other side, which is completely free zone for it, and can form a bond. So this is, let's say, my CH3, 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 O minus and this CH3. So this can attack from this area. There is no steric hindrance or no steric crowding from the chain, or its own bulky nature is not affecting its movement towards this hydrogen or bond formation with this hydrogen. So it has two options. One is this removal of hydrogen from beta 1, and second is removal of hydrogen from beta 2. Though removal of hydrogen from beta 1 will give it more stable product, that we also call it as a Sn2 product, but still it would not prefer going by that. Rather than that, it would prefer removing the hydrogen from the beta 2 position. Why? Because it is easier for it, because this is a very bulky base and will not be able to reach to this hydrogen due to its own steric crowding and due to the carbons present over here. So it will get repelled from these carbons, as well as it will get stuck due to its own heavy structure. So it will come to beta 2, will remove the hydrogen from there, and will form the less alkylated alkene, which is definitely a less stable product as compared to the Sn2 product, but that will be major. Okay, so the product form would be, again there will be two products possible. So two products will be formed. One is the Sn2 product, which will be this, and the other is Hoffman product, which will be this, but the Hoffman product will be major in this case. So you have to remember this. This is minor, Sn2 is minor, and Hoffman is major. So this is one important case where your Hoffman product will be major, whereas Sn2 product will be minor. Now, instead of this CH3, 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 there can be any other R group also, making it further more bulky. More bulky your base would be, the percentage of Hoffman product will keep increasing, and the percentage of Sn2 product will keep decreasing. Now, let's see another case where your Hoffman product will be major, whereas Sn2 product would be minor, and that will depend upon the leaving group. What leaving group is present on the carbon chain? So let's see. Let's take the example of this chain. Let's say I have fluorine over here. This is hydrogen. This is also hydrogen. This is beta 1 and this is beta 2. And I have a normal base over here. Let's say RO minus. Right? Now what will happen? This RO minus would try to form a bond with this hydrogen, or would try to form a bond with this hydrogen. So it has option of removal of hydrogen from beta 1 position or removal from beta 2 position, and simultaneously, according to the E2 mechanism, F should leave. But that doesn't happen very easily. Why? Because F is a very poor leaving group. So even though this RO minus would be attacking on hydrogen, F will take its own time to come out or to leave the system. Okay, so in that case, when the F is still present and your RO minus is trying to form a bond, just understand this. It has, this F has pulled the electron density. Okay, so here you will have a partial positive charge. Here also you have a partial positive charge on beta 1 and beta 2 carbon. But where do you think the partial positive charge would be more? Partial positive charge is more on beta 2 or beta 1. So it will be more on beta 1 as compared to beta 2. Why? This is because we have a CH3 over here, which is giving the electron density to this beta 2 carbon by its inductive effect. From this inductive effect, this partial positive charge is getting little nullified or getting little stabilized, because the CH3 is giving its electron density to this, whereas this beta 1 carbon has nothing to give the electron density, and hence this partial positive charge on this beta 1 carbon will be more as compared to beta 2. So which carbon will able to remove its hydrogen easily? or will be, because this carbon, these both of the carbons have partial positive charge, they will try to reduce their positive charge, or they will try to nullify their positive charge. And how will they do so? By breaking the bond with hydrogen. So they'll kick out hydrogen. When the base would be taking this hydrogen, the reaction will become more easier, because carbon is already getting a positive charge, base is attacking on it. From where the removal of hydrogen will be easier? Wherever the partial positive charge on carbon is more. So partial positive charge is more on this carbon, because there is no other stabilizing factor next to this carbon. Hence, removal of hydrogen from this beta 1 position will be easier as compared to removal from beta 2. Because this carbon also wants to nullify its positive charge, right? And this carbon also, but this carbon will not leave this hydrogen easily, because it is getting enough electron density to stabilize its partial positive charge from this CH3, whereas this beta 1 is getting nothing from the neighboring sides, no electron density from the neighboring sides to stabilize this partial positive charge. So this carbon will also try to break the bond with hydrogen, and base is anyways attacking on it. So what will happen? Removal of hydrogen from beta 1 position will be much faster than removal of hydrogen from beta 2 position. So base will be able to pull out this hydrogen faster as compared to this hydrogen, and hence the product which will formed by attack of base will be this as major as compared to this. So even though this is a less stable product, this is a Hoffman product, and this is less stable, still the rate of formation of this will be faster, or this product will be faster as compared to this product. So this will be Sn2 product, and this will be minor but more stable, and this will be major. So these are the two cases where your Hoffman product will be major. What are these two cases? First, you have a big bulky base which is quite sterically hindered in itself. And second is when you have a very poor leaving group attached to it, which is not leaving the carbon chain easily, and hence creating the partial positive charges on the beta carbons when the base is attacking on that hydrogen. Okay, so these are two cases where our Hoffman product will be major. Otherwise, in E1 and E2, both our Sn2 product will be major. Now what we will do some questions, we will understand, we will try to apply all these concepts what we have learned in these questions, and we will see whether we have understood or not. So I'll quickly write down some questions, try it on your own, and then I'll discuss.